All right. So in this video, I'm going to attempt to explain to you guys where this formula comes from, the formula for the coefficient of determination, with this interpretation here. Okay. Remember, it's just R squared. So I mean, if you can calculate the correlation coefficient and you square it, that's the same number. But if we think about it using this formula, we can kind of understand a little bit why it is a measure of the variability in long jump distance that's explained by the linear model. All right, so to explain what this means, let's revisit the sprint time versus long jump example, okay? Um, just to recall, this is 12 data points about how fast people can run and how far they jump. So let's take a look at the data set. Let's take a look at the scatter plot. Oops, sprint versus long jump. Okay, so if you know nothing about a person's sprint time, then what's your best guess for predicting their long jump distance? So if I don't know anything about sprint time and you had to give me a guess for what, just some random person, how far they'd jump, here's a vertical plot, dot plot of the data values. You'd probably make a guess someplace in here, right? Someplace in the center. And that would be actually the mean of your jump distances, jump mean. In fact, the jump mean was 124.6. That would probably be your best guess. However, you're going to have some errors. You're going to have a lot of errors. For example, this point here, that's going to be the error in your prediction. This point here, that would be the error in your prediction. So how could we quantify our prediction errors? Well, we could measure the distance from the mean. We could take each jump value and subtract it from the mean. And then like we do when we do the standard deviation and when we do the residuals, we could square that so that we don't get canceling values that sum to zero. So this squared value is a measure that quantifies how much variability there is in our estimation, how much error there is in our prediction. So let's calculate that number. Let's not, in this case, divide by the n minus 1 and take the square root of it, okay? I don't want the standard deviation. I just want to have a quantifiable number for my errors. So how are we going to do that? I guess we could just open up a new document, a calculator document, and we could just run the one variable statistics on jump lengths. Remember, this is the standard deviation here. But if you recall this last variable they put in, and you guys might have wondered why that was an important one to report. Well, in this case, it kind of is. This is the sum of the squared deviations from the mean. So 16,816.9. 16,816.9. Okay? So this is a measure that quantifies how much prediction there is when I don't have any second prediction variable at all. Okay? So now let's actually do our regression model. Now we use sprint times to make our predictions. And instead of getting prediction errors like this, I only get prediction errors that are like this. So I have less errors in my prediction. So let's quantify how much leftover prediction error there still is. Well, to do that, I'd want to know the difference between these values, which is my jump actual minus my jump predicted, which is my residual. And then to kind of be consistent with this squaring so we don't cancel out our values, let's just square those residuals. And let's add them all up, just like I did up here. By the way, these were the sums. So I want to find my residuals, I want to square them, and I want to add them up. A couple ways we could do that. First of all, let's calculate our residuals. When I run my linear regression line, it stores my residuals into a list, right? It stores them into this list right here, stat resid. So I could do the one variable statistics on that and take this bottom number again, or I could actually just square all those values and sum them up. Doesn't matter how we do it. I guess this one I'm going to do it by hand. I'm going to take the sum of my residual list squared. So what this is going to do is it's going to square my residuals, and then it's going to add them up. Easy enough. 500696. 500696. So this is a variable that quantifies how much air is left over when I use Sprint to predict my jump. And as you can see, this is less than this, meaning I had a lot of variability in my errors, and now I have less variability in my errors. In fact, I could figure out what percentage is left over. I could take the 5006.96 and divide by the 16816.9. I could take this divided by this. Oh, dope, 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 dope. Enter. Oops, oops, I'm sorry, I did that the wrong way. Dang it. I was doing so well too, and I screwed it all up. Let's take the small minus the big maybe. Does that make a little more sense for a percentage? And I get 29.77. Oh, I had it right here. I just did it wrong there. 0.2977 or 29.7.8%. So what this tells me is if this was 100% of the variation in my y's, now I just reduced that variation from 100% to 29.8%, meaning this linear model accounted for 1 minus that. So it accounted for 20.2%, 70.2%. So to summarize, if any of this makes any sense at all, here, when I didn't have a predictor at all, this is how much error I had. 100% of the variability in y was unaccounted for. But when I made my linear model and used sprints to predict it, it lowered those errors, the variability in my jump to this much, meaning 29% of the variability of y is now left unaccounted for, which means that my model accounted for 70.2% of the variability in y. And that's exactly what this formula is. It's 1 minus, this is the sum of the residuals squared, divided by the total squared errors whenever you just use the mean to predict it. Okay? So that's why this interpretation is what it is. Okay? But again, you don't really need to know this at all. You just, on the AP test, you really just need to kind of spit out something that sounds kind of like this. Okay? All right, let's look at an example. I'm going to put it to the next video for the example, though.